So now that we've introduced the basic machinery to quantify measurement uncertainty and preparation uncertainty, we can compare those. So conceptually, I think I showed that they're really different things. But now we have a uniform way to quantify both, right? And I'll just recap just that very briefly. So this is based on a metric, D, on outcome spaces, on each outcome space, right? So they could be different, they're not related, right? So on each outcome space, and also an error exponent. So therefore, because we have the same metric and the same outcome spaces in two cases, we can pick two observables. So pick observables A, B, right? And then let's maybe just to have a notation for that, right? Say if rho, so rho circle A would be the outcome distribution that I get when I prepare systems according to rho and measure according to A. So that gives us some outcome distribution on some space X, right? And the spaces for the different observables could be different. So just to have a notation for that. So preparation uncertainty is anything that describes this diagram. We draw the variance of the outcome distribution of B over the variance of the outcome distribution of A. And I defined the variance, just recall that, so the delta, or the spread, I should say, it's not the variance, it's the spread, right? So this is actually the minimum of the distances from mu to any point measure, right? So then if you compute that in the case of the quadratic means, then you get the usual notion of variance and mean square deviation. So that is the quantity at diameter. It's a one particle quantity. It's something that depends only on one distribution, namely these outcome distributions. And then we get some set, right? So maybe something like that. So everything above here would be possible to get by choosing appropriate input states. So now for measurement uncertainty, I'll use the same diagram, the same axes, the same units, right? So before, every point here was related to one possible input state. Now, every point in the diagram will correspond to an attempted joint measurement, right? And they have their errors. How did we define the errors? So first of all, if I have two observables, I define their distance, let's say of A and A prime. I define as the largest distance in the sense of transport metric between the output distributions. Right? So that's, and I have to take the supremum over rho, or the maximum. I don't want to discuss whether this is attained or not. Usually it is. So this is the distance between two observables, and now we are thinking one point here would correspond to a joint measuring device that has an A prime, or the marginals are called A prime and B prime, right? So really this is like the A and B. It's a joint measurement. It has two kinds of outcomes, and if I ignore one, I get the marginals, right? So every point here corresponds to one of these guys, and then on the axes I can draw, of course the A prime depends on what the joint measurement is, right? So So then on this axis, I just write the delta of A prime. And on this axis, I write the delta of B prime, which is a corresponding thing, right? So I get a green point here, right? There was already a green point here. I get lots of those. Now this is another area, and maybe it looks like that, right? But they're living in the same diagram, and I can sensibly ask, how are they related to each other, right? And that's the question I'm going to address. So it's not the conceptual comparison that's done, but the quantitative comparison, how do these diagrams compare? That's another story. That's the story I want to tell you now. Okay? I already mentioned one case of this comparison, right? So one, let's say, easy case, right? Those are the Fourier pairs. I'll explain a little bit more what I mean by that abstractly, maybe slightly more abstractly. And the metric that we choose, in these cases, actually the outcome spaces have the structure of a group. You can add things, like so the position is in Rn or on the line if you just take one component, and there is a distance that is translation invariant. So there's a notion of translation. And so the metric, and this, we take the metric to be translation invariant. This is important, otherwise it's not so easy. So D is translation invariant. So in that case, it's easy because the two diagrams that I was showing in the same coordinate system, the measurement uncertainty diagram and the preparation uncertainty diagram, they are just the same. Right? The uncertainty diagrams are equal. That's certainly not true generally. Actually, you could say it's because of the high symmetry here. So how do we go about this? How can we see that? The first thing to notice here is that the optimal joint measurement can be made also to respect the symmetry. Right? So optimal joint measurement can be taken covariant. If I shift the momentum in the usual quantum mechanical way, then also these distributions shift, and the same for the momentum is shifted and the position is unchanged. Right? So and the same goes the other way around. So that is the property of covariant observables. And then this has to be shown by averaging, and the key input here is that the criterion respects the group symmetry, and in this case there is no symmetry breaking, you could say it like that. So the optimal joint measurements can be, or the joint measurements, good joint measurements can be taken from the set of covariant ones that also respect the group symmetry. Now this also means that the marginals have this kind of property, right? So they also collaborate with the translations. So the marginals are then of a simple form. Well, and the form is addition of noise. So addition of noise works like this. So I have any kind of signal. In this case, it's a quantum state, or it's a quantum state, and I make a position measurement, let's say, that gives a number. And then the marginals always have, because of this kind of covariance, the marginals have to look like this. So there is a noise source, and I should call that the Q noise. It's the noise that describes the Q marginal, right? And this is just a noise source that has nothing to do with the input state. It's just an independent thing. but we take these two signals, add them, and that is the overall result. Right? So this whole thing, this whole box would then be called Q prime. Q prime is one of these guys. Technically speaking, if you look at the output distribution of this Q prime thing, you take the output distribution of the Q thing, you could just make a standard position measurement, and then you add noise. So there is something like, let's say, mu star, this is the convolution. So this is the noise. The convolution operation between probability measures corresponds to adding independent random variables. So this is exactly what happens here. We are adding independent random variables, and this is how so any process by which I get this translation invariance will have this property. Right? So it's only a consequence of the covariance. So now the problem shifts a little bit. So rather than understanding, we have to understand what these noises are. So if I make a covariant joint measurement, what are the possible Q noises and what are the possible P noises? And it turns out that the Q noise for any joint measurement is of the form sigma output distribution of another quantum state, and the P noise for the other marginal is the corresponding momentum distribution. So therefore, so this equality holds for arbitrary metrics and so on. It's extremely general, arbitrary metrics, arbitrary error exponents, and what have you, right? And the core fact is this, that actually the trade-off that we have for the noises in such marginals is exactly the same as the trade-off we have in the distributions of quantum states. So, of course, then I can ask uncertainty questions and then quantify that somehow. And I gave the inequality in the talk about transport metrics that shows that this is actually, so the distance between these two guys is then the size of the noise, the deviation from the zero delta function of the noise. And this shows that preparation uncertainty and measurement uncertainty in all these cases have to be the same. What we're using here to show that is this translation symmetry, which is extremely strong, right? Now, maybe, I don't want to go into many details here about what is a Fourier transform, but let me just mention to what this implies, right? So Fourier pairs are generated in the following way. So the Q would be, or the corresponding outcome space actually is a locally compact, forget what that means, abelian group. So we can have this addition structure. And the P would be in its dual, in the Pontryagin dual group. So in other words, the continuous one-dimensional representations of the translation group are functions of the form e to I kx. And so the k there is the momentum. This gives you all continuous characters of the translation group, and momentum is just a dual of that. Right? So this is the standard case, but this group could be anything. So any in this class, and in particular any finite group. So examples. One of the observables, Q, could be something like sigma z. Then you're measuring whether spin is up or down. This is a group, right? Because the adding, one of them is called the neutral element, the other sort of flips. And P would then be represented by sigma x. So this is basically a qubit. So qubits are actually Fourier pairs. If I look at them like that, if these are my observables, then everything that I said applies, and this inequality holds. Or you could say Q is angle, so it's a phase, right? And P would be the number. So phase number relation, angle number would be the same. Or many qubits. So like going from R to Rn, you also go from one qubit to many qubits, or qubit strings. Actually, also pretty popular in quantum information are QDITs, pretty bad terminology because you shouldn't make formula letters part of a word. That means d-dimensional quantum systems, so higher dimensional. And that's the same. You get a finite cyclic group as a group, and it's dual, which is isomorphic to that for the dual group. So this actually covers many interesting situations. So these are the Fourier pairs. And for all of those, the comparison is actually inequality. Okay, so let's look at cases where we don't have equality. So the Fourier pairs look deceptively simple, actually. So if you read Heisenberg, he doesn't even make a distinction here at all. He's just talking about knowledge in an unspecific way. After we showed these things with the Fourier pairs, we thought that maybe it's generally true. Right? So maybe always these diagrams are the same, and we would have learned something, but that's definitely not the case. So here's one simple argument. So not always the same. And one idea where you can immediately see that these are but that these are different properties, right? Is all these notions, they work with projection valued measurements. So when the yes/no measurement belonging to a subset of the outcome set is a projection always, right? Those are the projection valued ones. Or they could be just positive operators, POVM in the jargon of quantum information. So actually there could be some noise in the measurement. So noise in the measurement. Well, what happens when you look at preparation uncertainty? Preparation uncertainty is the task to make the distributions as sharp as possible. Now, but if there's noise in the measurement, you're messing up things in the first place. So the measurement itself has a certain noise, and certainly the noise in the measurement makes sharp preparation harder. So let's say it makes preparation uncertainty larger. So what happens to measurement uncertainty? Well, if the observables that you want to jointly measure make more fuzzy, they actually might become exactly measurable. That's the whole point, actually, of measurement uncertainty. You look at some proposed joint measurement. Now, if that were already the measurements that you have, they would be more noisy, as you saw in the previous example. There, it's very striking that you're just adding noise, right? So, so the more noisy measurements are actually exactly measurable jointly. So the uncertainty, the measurement uncertainty in the sense I defined, is zero, right? So it makes measurement uncertainty smaller. So from that you see that in some sense they're opposite properties. They're not. There's no reason why they should be the same. And in general, for general not projection valued observables, actually the more noise you have in the measurement, the smaller the measurement uncertainty becomes, but the larger the preparation uncertainty becomes. Right? So one important example here. Now let's go away from this case of generalized, that is POVM measurements, and just let's look at a particular projection valued case. Right? Example: measuring bases. So this is sometimes called a complete von Neumann measurement. So you have a basis, and you measure the one-dimensional projections that belong to that basis. Right? So those are the operation elements. So these are your observables, and you take two different bases. Then the preparation uncertainty. Well, it's not a single number, the preparation uncertainty, but by that I mean that in this uncertainty diagram, the origin is a possibility. So you can find states, the statement is, you can find states for which both variances are 0. Now, when is that the case? When you have measurement basis. So this is the case if and only if bases. So measuring basis, let's say E, A, that would be the A, and the basis F, that would belong to the B, right? So bases E, F share one vector. Up to a phase, let's say. And so if the two bases have one vector in common, that one will be variance-free, dispersion-free for both of them. So that's pretty trivial. And that's the only case where that happens. Now, measurement uncertainty is 0 if and only if. Well, we know that in general, joint measurability, that would be the case of measurement uncertainty 0, for projection valued measures just means that they commute. And so that if the two bases commute, they just have to be the same, right? So bases are the same up to permutation. That's a much stronger condition, right? So here they only have to have one vector in common. Here they have all vectors in common, and you just have to label them properly. Here you can generate tons of examples where preparation uncertainty is 0, but measurement uncertainty is definitely not 0. Right? So there is no joint measurement, even though there is a joint vector. So yes, we have many examples where these are different. And this example in the end shows that measurement uncertainty tends to be larger. Okay, so that will be my final remark and theorem. So on the note of general comparison of preparation and measurement uncertainty, there's one general result actually, and that is for projection value measurements in a finite dimensional Hilbert space. Let me give a loose statement first. That would be that measurement uncertainty is lower bounded by preparation uncertainty. So again, these uncertainty quantities are not just simple numbers, they actually refer to the diagram. So the precise meaning of this is precisely what we show is the convex hull of let's say the preparation uncertainty region contains the measurement uncertainty. That's a bit of a strange statement because what does the convex hull have to do with it? Well, it's part of the method of proof. We're looking at linear lower bounds, and then effectively you just get always discussing the convex hull with that method. So that would be something that is in the method of proof. But we actually have an example, very low dimensional, very easy, right? So everything can be fully computed. Using semi-definite programs that we also developed for this case, where actually the theorem is false without the convex hull. So here's the example, and you can see here the different regions are plotted, so they can be different. Another curious thing about this theorem is this constraint. Now, if you know my work, you'll think, well, why would this guy do anything in finite dimension if it can be done generally? Well, we can't. And so it actually is used in a certain essential way. In some sense, you use that there is the identity is a possible density matrix, and that is not, of course, not true in infinite dimension. We have a substitute for this, and that's a very, very subtle property of observable algebras involved that we're also discussing a little bit. But in general, for general infinite dimensional spaces, at this point, I don't even know if it's true. So that's an open problem here. And so thank you for your attention.